Okay, so in subtopic 2.2, equilibrium yield, in the first part, I would like to cover this stuff. Chemical systems may be open or closed. Now, for you to have equilibrium, you will learn that it needs to be closed system. Second one, over time, reversible chemical reactions carried out in a closed system at fixed temperature eventually reach a state of chemical equilibrium. So there are a few keywords there: closed system and also fixed temperature, which will be quite important for you to keep in your mind when we deal with equilibrium calculation later. Okay. Third one, the changes in concentration of reactants and products as a system reaches equilibrium can be represented graphically. What you need to be able to do is to draw and interpret graphs representing changes in concentration of reactants and products. So concentration versus time graph. Last box there, the position of equilibrium in a chemical system at a given temperature can be indicated by a constant Kc. Kc, it's called the equilibrium constant, related to the concentrations of reactants and products. So what you need to be able to do is to write Kc expressions that corresponds to given reaction equations for homogeneous equilibrium system, homogeneous one. And also to undertake calculations involving Kc and initial n/or equilibrium quantities of reactants and products for homogeneous equilibrium system again. So you do some calculations in here. Next slide is something that I want to cover in the next session, so maybe not today. All right. So what it means to be chemical equilibrium again. Now, a bit of this was covered when we were looking at the ion exchange chromatography, if you remember. Okay. So hopefully you remember a few things from that. Most reactions are reversible with a forward and backward reaction, just like the video that we saw, which there's a link there, same video for what if molecules were people, that video. Do you remember that? The people bumping into each other and, you know, gets attached to someone else's face, that's considered product. There was also a book dropped as well, that's the energy representation. What symbol is used to show that the reaction is reversible? Yep, double half arrows, okay? So draw that. The symbol of, you know, double two-way arrows, two-way half arrows are used to show that it's at the it's happening both way instead of just one-way arrow that you are used to use, okay? To show the reaction occurs both forward and backwards. When reaction is at chemical equilibrium, what is happening is, well, chemical reaction is still happening, okay? But there is normal color change, normal product being produced, normal gas may be coming off if it's in a closed system. That's because at equal rates, the chemical reactions are happening at equal rates, okay? It appears that no reactions are occurring. Try to picture this. My example that I usually give is dissolved amount of carbon dioxide into fizzy drink, okay? When you buy a bottled drink, unless you shake it, there's not much of gas coming out, okay? Because the system is closed. Cap is tightly sealed, so no gas is escaping. So even if gas come out from the drink itself, there's only a tiny part of air, you know, trapped in the bottle. That's the only place that gas can go, isn't it? So what's going to happen to the gas that's already in the little space that's available? What would those molecules do? re-enter might be a better word because it's not really a reaction too. The gas in already in a gaseous state would also try to go back because the pressure builds up. Yeah, so there is this equilibrium of gas try to be gas instead of dissolved CO2 dissolved in the drink. That happens at the same rate. But once you release and open the system, what's going to happen? Gas would try to escape. Yeah, because for the carbon dioxide to be trapped in the water, it's not natural. It's more energy consuming. Okay, it wants to be the gas, right? So that's a notion of system, and also closed and opened. Okay, so if you wanna take a note of that there too, that'd be good. The reaction is said to be in dynamic equilibrium. So even though you may not see any bubbles coming out from drink in a closed fizzy drink bottle, okay, it's not really a reaction, but gas dissolving into water and gas evaporating from water, coming out from water, is happening still. All right, it might not be visible to your naked eyes, but it's still happening. So, last summary there. For reaction to reach the equilibrium, the system must be closed, okay, where no reactant or product can be lost, and also at constant temperature. Okay. Now, if you change the temperature, equilibrium will definitely shift to either direction. Okay. So if you want the system to reach the equilibrium, it needs to be at constant temperature. All right. Dynamic equilibrium, a bit more explanation on that. So while a reaction in equilibrium shows no observable change, what you need to know is that there's something still ongoing. It's not static. Constant motion between reactants and products. Rather, the rate at which reactants and products are formed is steady. So the rate of reaction, rate of forward and backward reaction is steady. That's what it's saying. Dynamic means there is a constant interchange between reactants and products, and this is kind of like a person running up and down, running up the down escalator. And here's an image. So man is trying to move up, but you wouldn't see him, moving to upstairs as quickly as he can be. Or if the rate is the same, he would be staying in the same position even though he's running. Or escalator is, going backwards. So if you were able to measure the concentration by, looking at pH, you are able to plot this kind of graph, okay? Concentration versus time can be also used to show the chemical equilibrium of reaction. These graphs also show the ratio of product to reactant at any time there, yeah? When drawing these, make sure the lines are neat, and once equilibrium reached, use a ruler to draw the line. Now, it is important for you to be able to do the vertical line that shows the equilibrium with a ruler. Once the the concentration becomes flat, okay? So that you can show that the concentration hasn't changed from that point onwards, okay? And label the line as equilibrium. All right, so that's what you need to be able to do for concentration versus time. All right, let's apply all the things to this reaction. So consider this reaction. You've got 2HI becoming H2 and I2. Oh, that's an old format. I forgot to fix this one then. The arrow there is not, what you really should be using. 2 half arrows, please. Okay. So, 1. As the hydrogen iodide HI is heated, it decomposes. The rate of decomposition is initially high because concentration of HI is high. However, as HI concentration decreases, the rate of the forward reaction also decreases. This is because at the same time, the back reaction also occurs and HI concentration is less compared to the beginning. As H2 and I2 concentration increases, the rate of the back reaction will also increase, and eventually the rate of forward reaction will equal that of the back reaction. And finally, therefore, before equilibrium has been reached, the rate of the forward reaction is greater than that of back reaction. Now, series of explanation there, but this is logical explanation. There's a reason why I use numbering there as well. Okay, I'm being intentional here because you can probably use this explanation for your design prac, for your reaction as well. Okay, if you are able to work in a closed system though, okay, where nothing is evaporating. Okay, or if you could somehow contain your reaction, or if your reaction allows you to contain that. So this is an example of what you could be able to include in your next report. Okay? And also, this is also an interpretation example of the graph that you saw before. Okay? So if you're working with the graph, I'm expecting you to be able to draw the graph with Excel on your report, and you interpret it in these ways. Okay? All right. Let's go deeper. Explanation why equilibrium occurs. At equilibrium, the rate of forward reaction equals the rate of the back reaction. Now, if you were able to draw a graph for rate of reaction against time, okay, you would notice that the forward process and the back reaction, okay, forward and reverse reaction, backward reaction would end up at the same reaction rate. Okay, so the lines would merge. Now this is not the same as the concentration versus time. Yeah, this is rate of reaction versus time. Okay, at equilibrium, the rate of reaction becomes the same. Okay, let's simulate that. I need to upgrade my Flash player to do this apparently. Bear with me, the simulator will come up in a sec. There you go, cool. Okay, so what you're seeing here is a simulator for the reaction. And the graph that you are seeing is concentration versus time. At the beginning, before the reaction happens, at 350 K, 273, so 350K would be what? Fairly hot actually. Like what? 30, 40 degrees? It's not, yeah, it's just warm temperature, room temperature-ish. Okay. Volume is going to be 100. I could manipulate that too, but let's go with 100 to start with. So if you had 0.05, 0.05, 0.05, what's going to happen? Oh, actually, let's just do 5 molecules or a bit more. 14 molecules of HI to start with. If I click on, you should see the reaction happening. And I can still see that numbers changing slightly, but that's about that. Okay. So the green one that we started off was here. And there was no product of H2 and I2 before. So it starts at 0. Yeah. And the green one, we started off at there. And rate of reaction of its consumption was much greater here. And becomes less and less. The slope becomes flatter and flatter. And eventually becomes 0. No change from that point onwards. Okay. Because equilibrium would have been reached around there. So you need to be able to draw a line between here and there. Okay. Now, how many did I have here? I think I put 14, wasn't it? So you can see the decrease in number of molecules happened. And there was none in H2 and I2, but the same number of moles have been made. Now, at this temperature, that's what you see. At constant temperature, this is something that you would see. Let's say I raise the temperature a bit. At the moment, we only managed to see reaction, 0.04 as the product's concentration. But if I raise the temperature, see that equilibrium shifts. Okay. Now this is the reason why we've been saying that you need to work with a constant temperature. Okay. You can again picture the fizzy drink in a bottle, right? At warmer day, gas tends to expand. So the little spot that the bottle has at the top would have a lot more pressure on the hot day. So probably there's more tendency to be dissolved in the drink itself. But if you chill the bottle, the carbon dioxide in a gaseous state would probably have much less pressure. Therefore, probably there's more gas coming out. Okay? The rate of reaction of that is much lower, but in terms of equilibrium, okay, probably more gas is in the gaseous state. Sorry, CO2 is in the gaseous state. Does that make sense? Yeah. So same thing would happen to any reaction that would go back and forth. Okay. Alrighty. Observations of equilibrium. So during equilibrium, there are several macroscopic, which is something that you can observe, properties of a system that will remain constant. So if you're sealing the container, and if you can do that, or all the products and everything is in liquid state, temperature of the system would stay the same, pressure of the system would stay the same, color and pH would stay the same once the equilibrium is reached. Okay? So there's no observable change in that. And these should allow you to recognize that the system is at equilibrium. Or generally you might call it as reaction has finished. Yeah? That's what we've been saying. Reactions completed There's no observable change anymore. Color stayed as the same, and so on. Okay, but in fact, two-way reactions would still be happening. Okay. So in this case of this boat, water coming in, and this guy, checking the water away, there's no observable change in the amount of water in the boat itself. Yeah. Right. Depending on the reaction that you see, okay, sometimes product is favored. Sometimes reactant is favored. Okay, i.e., the backward reaction is favored. Now, in this case of gas A and gas B, right, A becoming B seem to be, in the first graph here, A becoming B seems to be a lot more favored compared to B trying to go back to A. Okay? How can you see? It's from the graph. A, which is a reactant, it decreases its concentration dramatically down to this, down below. And a B will increase dramatically as well. From that, you can say that this is a product-favored reaction. At equilibrium, the rate of reaction going back and forth would be the same. Okay, this blue range. Whereas if you flip, flip the reaction arrow, so you only start with the certain concentration of B, but no A in the system, see what happens. B gets, converted somewhat to A because the concentration decreases, yeah, but A doesn't increase so much, B doesn't decrease so much, yeah. That is showing that, A is still B is still preferred by this system for the reaction.
So A would rather change to B.
A would rather change to B, correct? Yeah, yeah. So B doesn't really want to go back to A. Okay. So this depends on which reactant you're working with or which reaction you're working with. Okay. Put this into some perspective. What's the reaction that you know which happens almost spontaneously? Or spontaneously. Something that you mix and just react. Salt and water? Dissolving? Maybe not so much. Something that you mix and it just either explode or just happens. If the reaction didn't happen, you couldn't do titration. That spontaneously happened, yeah? You didn't have to do anything. You didn't have to heat up or anything. What reaction did you use for titration? Neutralization. So you need, as reactants, acid and base. Thank you. So acid and base, they react spontaneously. They want to produce a product. Yeah, they spontaneously neutralize each other, yeah? Which would that be? Case 1 or case 2? 1, thank you. Because the product is always favored, yeah? So acid-base neutralization would be a good example of the first one. All right, can you think of anything that happens much more slowly or doesn't happen spontaneously unless you add some heat or something? So I'm trying to think of an example. I want you to think about an example for case number 2. Reactant is favored. water vapor. Sure, you can probably say that. You need heat, wouldn't you? Yeah, sure. Any reaction, that's state change.
What about splitting of water?
Sure. Yeah, we can do that. And we can look at both direction as well on that one. Yes, so think of hydrogen gas. Remember the popping test that you guys did in the past? Yeah? That happens spontaneously as soon as you put. So the reaction between H2 and O2 happens pretty much immediately, and it wants to produce water. Yeah? Hydrogen wants to take that energy in. Sorry, release that energy. Yeah? Whereas for you to create hydrogen gas and oxygen from water, what do you have to do? Put energy into it, yes. Like electricity. You can electrolyze water and get hydrogen gas and oxygen gas. That's exactly what this guy, yes. This does. Okay? I can provide electricity to this fuel cell, whether that's a solar panel or battery, okay? External source of energy into here. Then this will split water into H2 and O2. What I'm saying is that it requires energy for the reaction to happen. Okay? Water doesn't spontaneously want to separate into hydrogen and oxygen. Okay? That's why you should never put water into hot oil. Yeah? Can you picture what would happen to water? If you pour water into boiling hot oil, what's going to happen? Explodes because energy is provided to water and it splits to hydrogen and gas and oxygen gas, which would again react very vigorously. So reactant favored reaction example would be water becoming H2 and O2. Few more slides. So as I mentioned earlier, equilibrium is reached when the forward and back reactions are equal, like so. That's forward, that's backward. Could be the other way around. So the line meets and stay horizontal after that point. Okay, now classification of equilibrium. This is more for the background info. Just wanted you to know the difference between heterogeneous and homogeneous system. Okay, you wouldn't be tested on the knowledge on this, but you should probably know what hetero and homogeneous as well. Now, heterogeneous mixture would have products and reactants at different state. For example, BiOCl, which is solid, is reacting with aqueous solution of HCl, which would produce liquid water and solid. So they are in a different state, heterogeneous one. You won't be asked to find, say, Kc value for this kind of equation. The one that you get asked, and what you need to be able to write about Kc expression is this, what's called homogeneous equilibrium mixture. Reactants and products, they are in the all same state, such as this. CO2 gas, 2H2 gas, that would create methanol, which is in gaseous state when we were creating the methanol. Okay? So what you are asked to be able to do will be find what's called Kc value for homogeneous equilibrium mixture. And probably all the questions will be in homogeneous mixture, because I kept seeing that word in the description of what you meant to learn. Right, a bit of math here. Size of Kc? Kc is equilibrium constant, or it's also known as equilibrium expression. Okay, Kc expression. It indicates how far the reaction will proceed and proceed from reactants to products. We just talked about whether a reaction is product favored or reactant favored, forward reaction favored or backward reaction favored. Yeah, this is a numerical value which shows that. Okay, it's just that. The greater the value of Kc, the further the reaction will proceed to the forward direction. Okay, the value of, if the value of Kc is greater than 1, then forward reaction is favored. Then that also means, oh, that C is not in subscript. If Kc is less than 1, then backward reaction is favored. Okay, that's really that. So because the Kc value is found by looking at reaction like that, you got coefficient and also the species concentration. Yeah, coefficient of A is just 2 or 1 or whatever, and the capital letters showing the concentration of the species. Kc will be found. Sorry, if you do concentration of all the products using the coefficient as not multiplier, exponent of the concentration, divide by all that of reactants. Yeah, so products is always top, reactants at the bottom. Okay. Naturally, if products concentration was favored, products will be higher compared to the reactants. That means you will get a value more than 1. Yeah? If reactants concentration and all these values calculated was bigger than the products, then you will get a fraction which is much less than 1. Yeah? Meaning that reaction would prefer reactants direction. Okay? So product is always on top. Divide that by reactants concentration with coefficient used as exponent. Oops. Now, unit. You don't have to really give unit for Kc, because depending on what you're dealing with, depending on how many reactants and products you have, and how many times you multiply of each, okay, Kc expression's unit change. So you don't have to have any unit. You just have to give number as fraction if you're asked to calculate. Units for Kc change depends, yeah, as I said that. Let's do an example. So write Kc expression for the following: homogeneous equilibrium mixture. So you can say that this reaction is at equilibrium. How would you express Kc? So on the reactant side, you see 3O2 and 2O3, so that's ozone. So if you follow the formula that was provided earlier, you'd be just doing Kc equals to, what was you write? Products. Yeah. Now it needs to be in concentration, so make sure you use square brackets. Remember, square brackets means usually concentration. Products in this case is O3. So O3 goes into the square bracket. And what's the coefficient in front of O3? That's going to be an exponent. Okay? And you do the same for the reactant. So you would have the species, which is O2, and we are dealing with the concentration of O2. And what's the coefficient? Done. So that's how you show the Kc expression. Okay.
What do you do if it's on the
Sorry?
What if you do if it's on one? So like
On one.
if the reaction is less than one, it's it's favoring the backward reaction. But
Correct.
if it's
Yep.
greater than one, it's favoring the forward reaction.
Correct.
If it's on one.
On one. If it's on one, it means you would have a reaction that is very slow to occur because forward and backward is favored at the same way. Yeah. So depending on, there are certain equations like that. I'm kind of making this up, but think of rusting reaction. Rusting reaction. This happens very slowly. So you could argue that the forward reaction is favored, but at the same time, oxygen is not very much available if there is no water. So this reaction itself is very hard to occur. So you could also argue that backward reaction is favored as well at the same time. Yeah. So if there was water present, this will go much faster eventually. Yeah. Does that make sense? So if water was out of that equation, and if this was happening in a closed container, you could probably see a Kc value which would be very similar to, close to 1. All right. One more? Yeah. Last slide before we let you do next part of the stuff. All right. I've been talking too much anyway. Consider this equation. So HCl plus O2, that produces water and CO2 gas. Okay? What you are given is the number of moles which were present at the equilibrium and also before the reaction occurred. Okay? Write Kc expression first, then you will calculate equilibrium concentrations. Let's do Kc expression itself first together. I'll explain what the next slide would do for you. So let's do Kc expression on its own. Should still have 1 hour. Right, what would you write in this fraction? Where? H2O on the top, yep. Make sure it's in concentration exponent of 2. Yep, times. So just a dot is fine. Sure. Can someone else do the reactant part? Concentration of HCl and exponent of 4. Yep. Any exponent? Nah, just 1. So that's the Kc expression, okay? Now, for you to fill this up, and Kc is actually for the equilibrium, okay? You have to know the concentration of all these values at equilibrium first. But if you read the question, it only says at equilibrium 0.30 mole of CO2 was present. So you only know the number of mole of CO2 at equilibrium. So what you have to do before that is to calculate the equilibrium concentration of all the species, 3 other species, okay? For you to do that, you need to use rice. Think of me, rice. So when you ask to calculate equilibrium concentration, think of rice. Okay. Now use rice. RICE stands for ratio from chemical equation, so ratio of species. Okay? I is for initial molar concentration or number of moles if all of them are given in moles. C would be change in concentration, and E is for equilibrium concentration. And on the next slide, you would already see an answer. So let me just go through this before you look at the numbers, because I want you to go through it together. So hide that. Yeah, so remember RICE for finding equilibrium, equilibrium or initial concentration. All right, so this is what RICE would look like. Okay, use RICE to make a table and put the equation on top or species on top. Okay, Gabby, what's the mole ratio of the species?
That's what you've been talking.
Hmm?
That's what you've been talking.
No, just look at this. Mole ratio of the species. Mole ratio. So we are looking at stoichiometry here. What coefficient do you see?
Pull up. 4, 1, 2, 2.
That's it. That's all you need. 4, 1, 2, 2. Thank you. Okay. Shanae, initial number of mole was given in numbers. For HCl, what were you given?
0.8.
Yeah. O2.
0.4.
Yeah. Keep going. Water. So it's one of the products here. No, so there was none of that product. How about CO2?
0.1.
There you go. Good. So you fill up the information given. Fill up this table with the information given.
So are we saying there was no water used?
No water initially, before the reaction.
Okay.
Yeah. So I is for initial, yeah? So initial concentration before the reaction started, yeah, there was no water molecule. And one more information can be found on the question, which was, Yelena? Yeah, equilibrium concentration for CO2. So that's what you would put into the bottom corner there. Okay? Now, what do you think can be done from here? Alicia? Rest of the table. Where would you start with? Just look at this one. Do you notice 0.3 is here, and initially it was 0.1. So yeah, so change would be what? 0.2, good, and into positive direction, yeah, because it increased, yeah. What else can you find from mole ratio? What would be the next thing you would do, Ashley? Yep. So looking at 2. Correct. Yep. So H2O would have also increased by the same ratio. Yeah. So yeah, plus 0.2 is good. Therefore, what can be guessed on the reactant side, Oscar?
Would it be plus 0.1?
Ooh, would it be plus? 0.1 is good. Yeah, it's reactant. Yeah. Yeah, because you can see that the 0 changed to 0.2 will be here. Yeah, you can see that these reactants would have been decreased. Yeah, so negative 0.1. Hence, how much of HCl was consumed, do you reckon, Gabby?
I don't really understand.
Okay. Do you see the mole ratio which was done here, 4122? That's the ratio that you have to use to work out from this point. So plus 0.2 was created for Cl2. And if 2 and 2 are the same, same ratio would have been produced here. Yeah? And half of the mole of O2 would have been consumed compared to these. So 0.1 instead of 0.2. Okay? If one of that was consumed, you should have 4 lots more of that was consumed. Therefore, what will be the change? Correct. Minus 0.4. Now, if you know the change, you can then now do the calculation to find out equilibrium concentration. Okay? 0.3 already done. If you add 0.2 to 0, then you should get 0.2 as mole. 0.4 have been consumed by 0.1, so left over is 0.3, and same goes for here. 0.8 take 0.4, should be 0.4. Okay? So by using rice, you can find out how many moles have been left in the reactant side and generated. Okay?
How do you know if it's a minus or a plus? That's just the other thing.
When you look at the reaction, left-hand side is the reactants, yeah? So I assume to be consumed,
Okay.
yeah? And this side is a product, so assume to be produced, yeah? So produced ones should have positive change, consumed ones would have negative change.
Is there a case where it won't be like that?
Hmm.
And how do you know?
Looking at the change. So on this side, the information given was saying 0.1 mole for CO2 became 0.3. That's where you start working from. If this was a positive change, then you would have seen positive change for the other product as well. Yeah. And just follow along,
So if that was, so if the products were negative change,
Yeah. which wouldn't occur because water was 0 anyway. Yeah.
the reactants could be positive.
Could be, yeah. Could be. Depending on the situation. Yeah. If this same equation was shown with, I don't know, I'm just making this up again, but at much, much lower temperature, you may see a reaction going backwards, and that's favored. Yep. Okay, now this is where I stop and point out. Let's go up the slide. No, I've clicked too many times already. Here. What we meant to do, you are supposed to calculate the equilibrium concentration and calculate Kc. Now that you have found equilibrium number of moles, let's convert that into concentration, which you just have to divide by 10 because the vessel was 10 liters, yeah? Then put that in here. Okay? So, you know what I'm talking about? So in the table, what you have found, or you have the table there with all the answers, they are given in number of moles, yeah? You need to put that into concentration first. So divide that by 10 liters, yeah? So for example, if you saw 0.3 as equilibrium number of moles of CO2, 0.03 is what you should plot into the place of CO2. Okay? Then calculate Kc. Then you can say this was product or reactant favored reaction. After that, try doing 122 to 124.